Hi everyone, this is going to be the first lesson on the topic of waves for GCSE students of physics, and as the first lesson on this topic, it's going to be really a general introduction to what we mean by the term waves generally in physics. We're going to be looking at some examples of waves that are going to be explored in a lot more depth in later lessons of this topic. So speaking of this topic, let's just quickly take a look at some of the learning objectives here. Whether or not you're enrolled on this course on my website, you can always take a look at the learning outcomes or the learning objectives for each one of the lessons in each topic of each one of the courses. So this is on the topic of waves, as I say, and it's going to be the first lesson in this series, the general properties of waves. So this is what we're going to be taking a look at. We're going to start by looking at some of the general properties of waves in terms of amplitude, wavelength, frequency, and time period. And we're going to look at the relationships between these and how these are calculated and measured. We're also going to define these qualitatively and quantitatively, and we're going to be looking at the differences between transverse and longitudinal waves, and we're going to be modeling waves using some examples of waves, including ripples on the surface of water by means of a simulation of a ripple tank. And we're also going to look at longitudinal waves by looking at the example of sound. And so this is kind of what we're going to be going over, and hopefully by the end of this lesson you'll be able to describe, define, apply and do these various things. So if ever you need to remind yourself what you need to be able to do for this topic and this lesson, you can just go ahead and click on the Learning Outcomes checklist, go to this section, and you can find the learning outcomes here. So before we get into the general properties of waves, let's take a look at what we mean by the term waves in general. Now, I know that we have a few students, or actually quite a few students, attending this live stream, so I'm going to ask you guys the question. And those of you watching this as a recording on my website, the video will shortly pause so that you can answer this question yourself on the interactive pop-up. If you're watching this on YouTube, unfortunately, that's just not going to happen. So perhaps pause the video after this question and see if you can answer it for yourselves. So what do we mean generally by the word wave? So when the word wave is used in physics, specifically, what does it mean? Okay, I'm getting a few answers on the chat box on the live stream. Okay, great. Okay, so there's a lot of answers being given here, which they're all kind of pieces of the puzzle, and they're all kind of referring to various examples of waves, which is fine. But if we want to define the word wave in physics, we have to have a definition which covers all of the various different kinds of waves. So inclusive of sound waves, waves on the surface of water, light, electromagnetic waves of other types, and so on and so forth. So all of these are categorized as waves of various kinds. But the general idea of a wave, it always involves something which is vibrating. So it's always involving some form of vibration which transfers energy from one point to another, either through space, vacuum, or through some kind of physical material, some physical medium through which the wave travels. So if we want to summarize what we mean by the term wave in physics, it would simply be a phenomenon which transfers energy by means of vibration or oscillation. Oscillation is another word for vibration. So let's take a look at some examples of this, and we're going to make use of a simulation from the PHET website. I would encourage all of you to visit this website and take a look at their simulations. They are amazing. So let's start by waves on the surface of water. Now, most of you will have seen at some point this demonstrated in the school laboratory by means of a piece of equipment called a ripple tank. So what we have here is the surface of water looking down on the surface of water, and usually in the school science laboratory, this is illuminated from underneath with a light, so that as the waves travel across the surface of the water, you can see the crests and the troughs of those waves more clearly. So if we start a drip of water into the surface of this water, again assuming that it's illuminated from underneath, you'll start to see patterns emanating outwards from the point of impact of the drop, like this. Now these are waves being caused by the disturbance of the water at this point. The drops of water are causing the molecules of water at this location to vibrate upwards and downwards, and the forces between those molecules and neighboring molecules then transmits that vibration, which then travels across the surface of the water. Now, if we were to view this from the side, we would see something like this. So now it's more apparent, the shapes of the waves are more apparent as viewed from the side here. So we can use this to demonstrate what we mean by a wave, a particular form of wave, which we'll talk about a bit later, called a transverse wave. So we see here, at the point where the energy is being given to the surface of the water is vibrating upwards and downwards, away from the average position where the water was originally completely still and flat, to the maximum possible extent. And as the wave travels across the surface of the water, it loses energy, and the molecules at this point, for example, are vibrating upwards and downwards much less than they were at this point. So this is what we would categorize as a transverse wave, in the sense that the vibration at any point along the wave is upwards and downwards, while the direction of energy transfer is from this point outwards in this direction. And so transverse waves are categorized by the vibration being perpendicular to, or at right angles to, the direction of energy transfer. So if I reset this, so to begin with, the molecules on the surface of this completely still water are not moving. So this would be the average position, this would be the resting position. Now, if I start the molecules at this location into motion, we see that the energy is transferred away from this point in this direction from left to right. But if we were to place an object on the surface of the water at any point here, some floating object, that floating object would simply move upwards and downwards along the surface of the water. It wouldn't move from left to right. So the molecules themselves at any point along this surface are vibrating upwards and downwards to differing extents, but the energy is being transferred from left to right. So a transverse wave is one where the vibration or oscillation is perpendicular or at right angles to the direction of energy transfer. So this is waves on the surface of the water. Now we're going to be looking at some of the characteristics of waves, the measurable characteristics with which we can describe a particular wave, things like frequency and amplitude, a little bit later on. But for the moment, let's take a look at what these terms mean just in terms of looking at this model. So the amplitude of a wave is the maximum displacement away from the resting position at any given point on the wave. So at this point on the wave, if we show a graph here, we see that the displacement away from the resting position is much larger than a point further along the water's surface where the energy has been dissipated somewhat. So the amplitude is the maximum displacement away from the resting position in either direction, upwards or downwards in this case. And again, we'll be looking at what these terms mean a little bit later on. Now, the frequency of a wave, the term frequency generally is used to describe how often something happens, or in other words, the count of something, how many times you can count something happening per unit of time. So if I was to say that in the United Kingdom it rains more frequently than it does, say, in Africa, I'm not entirely sure if that's true or not, but I'll just use that as a hypothetical example. Then what I would be saying is that in any given time period, let's say in 1 year, if you count the number of times it rains in the United Kingdom, you're going to count more periods of rain than you would in a place like Africa. So when we say frequency generally in ordinary English, it means how often something happens. In other words, how many times you can count something happening per unit of time. Now in this case, it's also a similar definition. The frequency of a wave is how many complete waves, complete oscillations. So how many times the wave moves from the resting position upwards to its maximum extent, downwards to its maximum extent, and then back again, which would be one complete wave. How many times that occurs per unit of time. Now in physics, time is measured in standard units in seconds, and so the frequency of a wave is how many complete vibrations or oscillations there are per second. Now waves per second is given the unit hertz in physics, and so a frequency of 1 hertz would mean that one complete oscillation occurs every second. So given that we've just defined these terms, let's take a look at what happens to this wave when we increase the frequency. So if we increase the frequency, we're producing more waves per second, as you can see. If we decrease the frequency, we're producing fewer waves per second, as we can see here. Fewer complete vibrations upwards and downwards per second. If, on the other hand, we bring the frequency back to some moderate value here, and then look at what happens when we change the amplitude. Again, the amplitude of a wave is the maximum displacement away from the resting or average position. So if I decrease the amplitude down, we see that the displacement from the resting position upwards or downwards, the maximum displacement has decreased. If we increase the amplitude, we get a much larger maximum displacement that we can see here. So that's the meaning of these terms, and that's how they would appear for a transverse wave, like the wave that you see here on the surface of a pool of water. Now, there is another type of wave which we're going to be discussing, the longitudinal wave, and in general, waves can be categorized as either being transverse or longitudinal. So a transverse wave, again, is a wave in which the vibration is perpendicular to the direction of energy transfer by the wave. But waves like sound waves are a different kind of wave. In these types of waves, the vibration, the oscillation, is parallel to or along the same line as the direction of energy transfer by the wave. So this is a loudspeaker, and we have air here. And again, we're going to first of all show the waves like this. And so as the loudspeaker moves backwards and forwards, it's producing sound waves which emanate outwards in all directions from the loudspeaker. Now, longitudinal waves are different from transverse waves because in this case the vibration is parallel to the direction of energy transfer, and as we'll see in a later lesson on the subject of sound waves are transferred by means of the vibrations of particles of the medium through which they're traveling. So if we imagine this sound wave is traveling through air, and we could see the particles of air, some of these particles have been given a red color so that you can follow their motion more closely. So we see here, as the loudspeaker cone vibrates backwards and forwards, it causes the air particles to cluster together, to become closer together when it moves forwards, and move further apart from each other as it moves backwards. And so each one of these air particles is vibrating around a mean or average position. But as you can see here, if we pick this particle here, for example, it's vibrating around this average position here, but it's vibrating backwards and forwards, and this is parallel to the direction of energy transfer by the sound wave, which is in this direction from left to right. So this would be a longitudinal wave, and again, we'll be exploring sound waves in a little bit more depth a bit later on. So if we can see both of those representations of the wave, we can now see how sound waves and other longitudinal waves travel. So again, a longitudinal wave like sound is a wave in which the vibration is parallel to the direction of energy transfer. So let's take a look now at the general characteristics of waves, because all waves involve vibration. They all involve and any form of vibration can be counted in terms of the number of vibrations per second. And so we can define at least 3 quantities which can be used to describe a particular wave, be it a transverse wave or a longitudinal wave. So let's start with the idea of amplitude and give ourselves a definition. So the first of the 4 key terms that you need to, at least 4 key terms that you need to understand, would be amplitude. So amplitude is defined as the maximum displacement of the vibration away from the resting position. Now, this is a graph, not a transverse wave specifically. This is a graph where, if you imagine the vertical axis here being the displacement from the average position, and this line here representing time, then each one of these particles here, or any one of the particles in the wave, will be vibrating away from its resting position away in this direction or away in the opposite direction. And so these kinds of representations that you might see in an exam question or in the laboratory on a device called an oscilloscope, which we're going to be looking at later, these don't necessarily represent transverse waves, even though they do look like a transverse wave. These will often represent any kind of wave, because if we have a longitudinal wave, and again think of the wave that you just saw with the sound wave with the air particles vibrating backwards and forwards parallel to the direction of energy transfer, well, in that case the particles are vibrating to either side of a mean or average resting position. So if this is the average resting position and this axis of this graph represents the vibration away in one direction and away in the opposite direction, this graph could just as easily be representing a longitudinal wave as it could a transverse wave. So the amplitude is the maximum displacement of the vibration relative to the average or resting position of whatever it is that's vibrating, whether it's particles or something else. So the amplitude of this particular representation of a wave could be measured here, or it could also be measured here, because both of these are going to be the same value. They are both going to be the amplitude, the maximum displacement away from the resting or average position. Now, the wavelength. So if we now imagine that this is representing a transverse wave, for example, the wavelength is defined as the distance from one peak of a wave to an adjacent peak. It can also be described as the distance from one trough to an adjacent trough. However, you could also say that if you measured the actual distance in meters, standard units, from this point on this wave to the same point on the adjacent wave, that would also be the wavelength. So even though you will see this definition given for the wavelength of a wave in a lot of physics textbooks and online, a more inclusive definition would be the wavelength is the distance in meters from a specific point on one wave to the same point on an immediately adjacent wave. So from here to here would be one wavelength, just as much as from here to here would be one wavelength. So if you pick any point on a wave and then measure the distance between that point and the same point on an adjacent wave, you're going to get the wavelength. And again, because you're measuring a length, this is measured in meters or standard units. So the frequency of a wave is the number of complete waves that pass a fixed point in every second. So this wave that you're seeing here, this transverse wave, has a frequency of about 2 waves per second, or 2 hertz, which is abbreviated to Hz, capital H, lowercase z. So 1 wave per second is 1 hertz, 2 waves per second would be 2 hertz, and so on. So I mentioned that there are at least 4 key terms. We've mentioned 3 of them. The third of these is the speed of a wave, because waves transfer energy from place to place, and so because they are moving phenomena, their speed can also be defined. So the speed of a wave is simply the definition of the speed of any object. It's the distance travelled by the wave per unit of time. In other words, the distance the wave travels in 1 second. And again, the standard units of speed are, of course, meters per second. So all waves obey a specific relationship between their frequency, their wavelength, and their speed. This is sometimes referred to as the wave equation, and it applies to all waves, whether you're dealing with longitudinal waves, transverse waves, any variety of either one of those 2 waves. They all obey the wave equation, or the wave formula, which is this: that the speed of a wave is equal to the product of its frequency and its wavelength. So whenever you want to calculate any one of these and you know the other 2 values, you can use this equation. So again, this equation will only work if you have the correct units within it. So again, the standard units of speed of any object or any wave is going to be meters per second. Frequency is waves per second, or hertz, and wavelength, because you're measuring a length, the standard units of length, which are always used in physics, are meters. So let's take, for example, the speed of sound in air. Now, the speed of a wave is affected by the type of material that it's traveling through. So sound requires a physical medium to travel through, as we'll see in later lessons. Sound travels in air at about 340 meters per second and travels in water at about 1500 meters per second. Now, some waves, like for example electromagnetic waves such as light and X-rays and gamma rays and so on, they don't require a physical medium to travel through. They can travel through physical media. Light can of course travel through glass or through air, but it can also travel through a vacuum. But all waves will be affected, their speed of those waves will be affected by the material or lack of it that they're traveling through. And this leads to some of the other properties of waves that we're going to be exploring later in this lesson and also in subsequent lessons, namely things like refraction, reflection, diffraction, and so on. So I mentioned that the wave equation applies to all waves, and of course if you need to calculate one of those quantities in the wave equation, you may need to rearrange the equation. Now I realize that some of you have no problem with rearranging equations, but some of you benefit from the use of these formula triangles to help you remember how to rearrange equations. So for the benefit of those of you who need these formula triangles, this would be the one for the wave equation. The speed of the equation is given here. Speed is equal to frequency times wavelength. And if you want to rearrange this equation to find the frequency, you would need to divide both sides by the wavelength. The wavelength is given this Greek symbol lambda, which looks like a kind of upside down Y. So frequency is therefore going to be the speed divided by the wavelength, and if we need to rearrange this equation to make the wavelength lambda the subject, we would divide both sides by frequency, and so the wavelength is going to be the speed divided by the frequency. So feel free to use this formula triangle if you need to rearrange the equation. But of course, always when you're answering exam questions, it's good practice, whether you're using a formula triangle or not, to show the examiner how you've rearranged the equation before you start substituting values and calculating the answers to exam question calculations. So let's take a look at an example of such a calculation. So we have a blue ray of light. It has a wavelength of 475 billionths of a meter, 475 nanometers, or 475 times 10 to the power minus 10 meters. It has the speed of approximately 300 million meters per second, which is sometimes called the speed of light. So calculate the frequency. Going to give a few seconds for the students in attendance to have a go at this question again. Okay, it seems like most of you have, many of you have had an attempt at that. Okay, great. So let's walk through how we do this. This is pretty straightforward, but again, we need to look at an example anyway, so let's go ahead and do that. So in order to calculate the frequency, once again, you're going to need to rearrange the wave equation to make frequency the subject. So you would do it like this. Frequency is the speed divided by the wavelength. So frequency is therefore 300 million meters per second, the speed divided by the wavelength, 475 times 10 to the power minus 9 of a meter. Now again, make sure that these are in the correct units. If this was in nanometers, if you put 475 nanometers and just put 475 down here, you're obviously not going to get the correct result for the frequency. So this, when we evaluate it, gives us a frequency of 631 million billion of hertz or waves per second. Or more simply, we can just write this as 631 times 10 to the 8th megahertz. Now a megahertz, a capital M in front of any unit, is millions of hertz. So this M represents 6 of these zeros, and we need times 10 to the power 8 to multiply the 6.31 to get the remainder, the remaining digits of this number here. So we can represent this as 6.31 times 10 to the 8th megahertz. So We're going to be exploring sound waves in more depth in the next lesson of this topic, but let's just take a look at them here just as a kind of introduction to the topic of waves in general. So often you will see these demonstrated or at least modelled in the science laboratory by means of a slinky, and you can also model longitudinal as well as transverse waves by a metal slinky. So when we take one end of a metal slinky and move it rapidly backwards and forwards along the length of the slinky, we produce a longitudinal wave where when the slinky is repeatedly moved at one end, when you move it forwards, the coils of the slinky will bunch together, will compress like this, and when you move it backwards, the coils of the slinky will move further apart like this. Now, each one of these coils is simply moving backwards and forwards like this, but the energy is being transferred from the end of the slinky, which is being vibrated, towards the other end, and so you'll see these compressions and rarefactions, as they're called, moving along the slinky in this direction. So this is a very easy way of modelling a longitudinal wave like sound waves. In this case, each coil of the slinky represents one of the molecules of the air or whatever other physical medium the sound wave is travelling through. So, for example, each coil of the slinky would represent one of these particles where the particles are moving backwards and forwards. This loudspeaker is represented by the end of the slinky, which is being vibrated backwards and forwards. So, and the regions where the particles are moving further apart are represented by the regions of the slinky where the coils are moving further apart from each other, and the regions of the slinky where the coils are bunching closer together would represent the regions of the air where the particles of air are moving closer together and being compressed. So, longitudinal waves are composed of regions of compression where the particles are closer together and rarefaction where the particles move further apart, and this can be represented by means of using a slinky in this model here. So we have rarefactions and we have compressions, and this is the sort of language that examiners will expect you to use when you're describing sound waves. Now, when you're measuring the wavelength of a longitudinal wave, it's the same principle. It's the distance between one point, a specific point on one wave, and the equivalent point on the next wave. So we can measure from one compression to another compression. This would give us the wavelength of this wave. We could also measure it from the center of one rarefaction to the center of the neighboring rarefaction. Either way, you're getting a measurement of the wavelength. So sound waves are longitudinal waves, and they're generally produced when objects vibrate in any kind of physical medium, whether it's a solid, a liquid, or a gas. So a tuning fork, if you hit a tuning fork on a hard surface, you produce a sound, and the reason for this is because of the rapid vibration of the prongs of the tuning fork, which then set the molecules of air around them into vibration, very similarly to the way in which the loudspeaker cone, or indeed your vocal cords, set the molecules of air around them into vibration as they move backwards and forwards like this. Now, we mentioned light, which is a member of the electromagnetic spectrum. We're going to be getting into electromagnetic waves in a lot more depth in later lessons of this topic. But the electromagnetic spectrum is the electromagnetic waves generally are phenomena of vibrations of the electromagnetic field. Now, fields are a topic which are kind of prevalent all the way through GCSE physics courses. A field is a quantity which varies in direction and magnitude at all points in space around the object causing that field. So a gravitational field around an object like the Earth, for example, is going to vary in its strength depending on where you are around the Earth. If you're near the surface of the Earth, it's going to be relatively strong. If you're further away from the surface of the Earth, it's going to be relatively weaker. So the magnitude of a gravitational field varies, but its direction also varies. So if we imagine the Earth is here and you are located somewhere over here, the direction that the gravitational force will act in will be towards the center of the Earth, which will be in this direction. Whereas if you move around to over here, the direction of the gravitational field will be in this direction. And so not only does the magnitude of the field change depending on the distance away from the object causing the field, in this case the Earth, but the direction of the force of that field also changes. And so a field generally is a vector quantity which changes its magnitude and direction at all points in space around the object causing that field. Now, we also have things like electric fields, which we looked at in the electricity topic of this course, and they follow the same definition. If you have a charged particle, like a positive or a negatively charged particle or object, they have electric fields around them which will exert forces on other charged objects. The forces will vary depending on the distances between the charged object and the object causing the field, and the direction that those forces act in will also vary. And so magnetic fields, electric fields, and gravitational fields, and also other types of fields in physics, they are all just quantities which vary in their magnitude and direction around an object. Now, why am I talking about this in the case of electromagnetic fields? Well, it turns out that the electric and the magnetic phenomena are linked to each other. They can be described by in different ways, but they are related to each other. So wherever you find an electric field, you generally find a magnetic field, and so often we talk of them as though they're the same thing. And in fact, in physics, there is such a thing called the electromagnetic force. So electromagnetic fields are field phenomena. Now, just as with a gravitational field, the whole universe is permeated by the gravitational field, which is composed of all the gravitational fields and all the interactions between those fields, between all the objects with mass in the universe. In the same way, there is a electromagnetic field which is due to all of the charged and magnetic objects in the universe. And as with any kind of field, when those objects causing the fields vibrate or move, the shapes of those fields also change. And so electromagnetic waves are waves, they are vibrations in the electromagnetic field. So if the electric field is vibrating in this direction, the magnetic field always vibrates at right angles to it. So what you have when you're talking about light or infrared radiation or ultraviolet or X-rays or gamma rays, these are all vibrations of the electric and magnetic fields, which then carry energy through space. So when even though our bodies are set up to interpret these different things like infrared radiation and light very differently, so for example, we interpret light with our nervous systems as the perception of vision, because we have eyes with photoreceptors which are sensitive to the frequencies of electromagnetic waves in the visible range. But infrared radiation, which is heat radiation, is the same phenomenon, it's just vibrating less frequently, and yet our bodies interpret it very differently. So, even though all electromagnetic waves are the same phenomena, they are just vibrations of electric and magnetic fields, they are interpreted differently, and they have different effects on physical matter depending on the range of frequencies that you're talking about. And so the electromagnetic spectrum is a range of different frequencies and wavelengths of this vibration of the electromagnetic field, and it extends from very long wavelength, low frequency radio waves to very short wavelength, high frequency gamma rays at the other end of the spectrum. So for convenience, we divide these different ranges of frequencies and wavelengths into these broad categories of electromagnetic waves. But the thing to remember is that these are all essentially the same phenomenon. They are vibrations of the electromagnetic field which transfer energy through space. The only way that they actually differ from each other is in their frequencies and their wavelengths, and also what their effects are on physical matter. So at this end we have very high frequency, very short wavelength waves, and at the other end we have very long wavelength, very low frequency waves. So as the wavelength increases, the frequency decreases and vice versa. Now the reason for this is because of the wave equation. So if we take a look at the wave equation, we mentioned that the speed of a wave, including any kind of electromagnetic wave, is equal to its frequency multiplied by its wavelength. What this means is if the speed of a wave remains constant, now all of these in a vacuum travel at the same speed, the so-called speed of light. Light is just another example of electromagnetic waves. It's a very narrow range of frequencies somewhere in the middle of this spectrum, which our eyes are sensitive to, ranging from the relatively high frequencies of the blue and the violet down to the relatively low frequencies and long wavelengths of the visible red. When you go beyond the visible red, you get into the infrared range of frequencies. Infra means less than. And so these waves, these electromagnetic waves here, have a lower frequency than the visible red. At the other end, you have the ultraviolet. Ultra means beyond or more than. So this is the range of frequencies of electromagnetic waves at higher frequencies or shorter wavelengths than the visible violet or the visible purple. But in either case, visible light is a very narrow range in the middle. So this is what we mean by an electromagnetic spectrum, and we're going to get to later lessons in this topic where we explore each of these in a lot more depth and look at the electromagnetic spectrum in a bit more depth. Now, what these all share is obviously that they're all waves in the electromagnetic field, but they are all transverse waves. So as the electric and the magnetic fields vibrate like this, that vibration carries energy at right angles to the vibration. So if the electric field or electromagnetic field is vibrating like this, the direction of energy transfer is like this. So when you have objects like the sun, which are giving out most of these at various levels of energy, all of these waves are traveling outwards from the sun. And so if you imagine you have the sun over here and you have the earth over here, the sun is transferring energy to the earth, but the transfer is done by means of electromagnetic waves, where the electromagnetic field is vibrating like this, but it's transferring energy like that. So again, based upon our definition, that would constitute a transverse wave because the vibration is perpendicular or at right angles to the direction of energy transfer. So light waves have certain fairly intuitive properties, and these are shared by other members of the electromagnetic spectrum. They travel in straight lines, and a light ray, one of these rays of light that we see in this forest scene, consists of transverse waves in every possible plane. And so if the electromagnetic field is vibrating like this in one wave of light, another wave of light, it might be vibrating like that, another wave of light might be vibrating like this. And so all of these directions of vibration are possible for the rays of light coming from an object like the sun, but they are all moving. All of those waves are transferring energy at right angles to these vibrations. And so from this diagram, all of these waves would be transferring energy towards you at right angles to the vibration, which is drawn on the plane of this diagram here, or away from you. And so the actual energy transfer is always at right angles to the actual vibration of the electric and magnetic fields here. Now this applies to unpolarized light, light coming from an object which is unpolarized. We'll talk about polarization a little bit later, but that kind of is a bit more of an extension topic. So one of the properties of waves generally is interference. Now interference occurs when waves with the same wavelength and same frequency, which are generated from two sources which are close to each other, meet each other. So you can see here what two sets of waves on the surface of water, one coming from over here, one coming from over here, overlapping with each other. And if this is illuminated from underneath or above, you'll see these patterns being formed, and these are interference patterns. Now, Thomas Young, a very important scientist in many respects, discovered that light could actually show this same kind of interference. In Young's very famous double slit experiment, he passed a beam of light through two parallel slits in a screen, forming a pattern of alternating light and dark bands on a white surface. From his experiments, Young also suggested the wave nature of light, because he said, well, waves, like the waves on the surface of water, show this property of interference, and he had shown that light actually also shows this property of interference. And so he sketched what he saw on his screen, which reminded him of the interference patterns on the surface of water when you have 2 points on which the water was disturbed and the waves start to overlap each other. Now again, we can see this in either the school science laboratory or in a simulation here. So let's take a look at interference. So what we have here is 2 sets of spigots here to disturb the surface of our ripple tank. And if we set these into vibration, we can see that the waves emanating from them, again, if we imagine these are being illuminated from underneath or above, we can see the interference patterns here. Now, other types of wave will also show interference. So if we look at sound waves, for example, and we set these into vibration, and again, it's fairly clear when we represent them like this that sound waves also interfere with each other, but slightly less clear when we look at the particle diagram. So waves will interfere with each other in the sense that when you have waves of a similar wavelength and frequency from two different sources close by, when those waves meet each other, the crests of the waves will reinforce each other, which is called constructive interference. The troughs of the waves, when they meet each other, will reinforce each other. That's also constructive interference. Now, when a crest meets a trough, the waves cancel each other out, and this is called destructive interference. Now, again, light can also show interference. So if we imagine that we have two sources of light, both of the same frequency, and we model the light like this, we can see that they clearly form these interference patterns. Now, if we show this on a screen, if we project these lights onto a screen, we would see these dark and light bands where the waves are hitting the screen here. Now, the wavelength or frequency, which are connected to each other, will change the interference patterns. Now again, if you have waves which are traveling at the same speed, again, think back to our electromagnetic spectrum. All of those electromagnetic waves travel at the same speed. So V is a constant. But if you increase the frequency, so if we increase the frequency and we assume this is constant, well, in order to keep this side of the equation constant, by increasing the frequency, you have to decrease the wavelength. And similarly, if you decrease the frequency in order to keep the speed constant, you have to increase the wavelength. So, as you increase the frequency of a wave, assuming that the speed of the wave is not changed, you must decrease the wavelength and vice versa. So, if you change the frequencies, you can see that the wavelength will change, which means that the interference patterns will also change because the waves are either constructively and destructively interfering more frequently, or they're doing so less frequently. So we can see here that as you change the frequencies here, and therefore the wavelengths, we're seeing different interference patterns. But this experiment basically showed the wave nature of light. However, other experiments can show that light behaves like particles, and so we have two different types of model for electromagnetic waves. We can model them as particles called photons. We can also model them as waves. Both models, that it's not so much that one is correct and the other one is incorrect, or that both are correct. These are just both models of a real phenomenon, which are both useful under different circumstances. So, when we're talking about interference, when we have waves which are in phase with each other, the peaks will reinforce each other to produce bigger peaks, and the troughs will reinforce each other to produce bigger troughs. And so you produce a wave of a higher amplitude when you get constructive interference between two waves of similar frequencies and wavelengths. Now, if we take those waves and put them out of phase with each other, where a trough meets a peak and a peak meets a trough, we can see that they cancel each other out. This is called destructive interference. So we can also demonstrate interference by means of loudspeakers. We take two loudspeakers and we put them about 1 meter apart, and we get them to produce the same frequency of sounds, and we'll find that there are certain positions where if we take a sound detector, we can measure a low energy or a low sound level, a low volume, low amplitude, and other places where we can measure a higher amplitude. So these concentric circles around each speaker represent the peaks and the troughs, as shown here. The peaks are these solid lines, the troughs are these dotted lines. Now again, because we're dealing with a longitudinal wave, the peaks are the compressions, the troughs are the rarefactions. So constructive interference is represented by these little red dots here, where the peaks meet the peaks, or the troughs meet the troughs, and the destructive interference is represented by these blue dots, where you have a peak meeting a trough, or you have a trough meeting a peak. So at these positions, the measurable amplitude or volume of the sound will be lower than at these positions. So, whenever two waves will form constructive or destructive interference is determined by the difference in their wave paths. Now, here we're getting into a bit of an extension work, but after all, the whole purpose of these courses is to give you guys a much deeper and more kind of robust understanding of these things. So audio engineers, when they're designing a sound system for a room or something like that, they will take account of the positioning of the speakers so as to maximize the audibility of the sound, to minimize these spots where there is constructive interference and maximize or minimize the destructive interference and maximize the constructive interference. So if the difference in the number of half wavelengths of the two waves is an even number, this results in constructive interference. So for example, if we take two waves and we put them out of phase with each other by an even number of wavelengths, like this one here, an even number of half wavelengths, this will result in constructive interference, because as we can see here, a trough lines up with a trough on an adjacent wave, a peak lines up with a peak on an adjacent wave. If we then use another even number of half wavelengths, so this one would be 2 half wavelengths, making one complete wave. This would be 4 half wavelengths, making them 2 complete waves out of phase. You still get constructive interference. But if the difference between the two, between the adjacent waves in terms of half wavelengths is an odd number, this results in destructive interference. So if we use a phase difference of 1/2 of a wavelength like this one, we see that a trough lines up with a peak on an adjacent wave and a peak lines up with a trough on the adjacent wave. And so this results in destructive interference. Again, here we have 3 half wavelengths, an odd number of half wavelengths. And again, we get destructive interference here. So constructive interference in sound waves results in the sound becoming louder. Destructive interference results in the sound becoming quieter, and this is very much the same in the case of other waves, like light, for example. So in the case of light, as we saw on the simulation, the constructive interference results in the light becoming brighter, the destructive interference results in the light becoming dimmer. So let me just skip past this because we've just illustrated that. So again, this is another representation of the Young double slit experiment. So we have here light passing through 2 narrow slits, and it's monochromatic light. So we're using a filter to make sure that the light is all just one color, one frequency of light, or one wavelength of light. So if we start with the slits at 2 millimeters apart, we can see these bands here, these bands of light on the screen. And again, these regions are caused by constructive interference. These regions are caused by destructive interference, where these two sets of waves overlap each other. If we change the distance apart to 3 millimeters, we can see a different interference pattern. If we change it to 4 millimeters, we can see yet another different interference pattern. And again, 5 millimeters, yet another different interference pattern. So the interference patterns produced by 2 holes in a pinhole camera basically illustrate this same principle. So this was this is a very old but still functional pinhole camera, and it produces this interference pattern on the screen at the back of the camera, where light is allowed to pass through these 2 pinholes. Now, I mentioned that light coming from any given source, such as a light bulb or from the sun, the electromagnetic waves vibrate in all different directions. They're all coming from the sun to the earth, but they're all vibrating along different axes of vibration. So that would be described as unpolarized light, but you can polarize the light. You can pass light through materials which only allows the electromagnetic waves, which only allow through them the electromagnetic waves which vibrate in one specific direction, and this gives rise to polarized light. So again, in a beam of sunlight, the vibrations take place at every possible angle. So if we imagine a beam of sunlight coming directly at us here, then the electromagnetic vibrations, which are the waves of light which transfer the energy, they are vibrating at right angles along all possible planes along that wave, which is along that beam of light which is traveling towards us. But in a beam of polarized light, the vibrations take place in a single plane only. So, for example, along this horizontal plane. Now, this is the effect of polarizing materials. So Polaroid sunglasses, for example, and also polarizing filters for cameras, they produce their effects by filtering out all except for one plane of vibration of light rays. And so if we look at an image viewed through through no polarizing filter in a camera versus one which is viewed through polarizing light, you might see this kind of image difference. So in the picture on the right, the polarized light has blocked out reflected sunlight and all rays of light which are vibrating in any other direction except that one direction. And you can see that this has an appreciable impact on the image. So polarizing filters polarize light because they're composed of long chain molecules, polymers, which are aligned within the filter in the same direction. So for example, in a particular filter, the molecules that make up that filter may be aligned all vertically, and this allows only light vibrating in one particular direction to pass through the filter and absorbs or reflects all the other directions of vibration. So as unpolarized light strikes the polarizing filter, the portion of the waves vibrating in any plane other than the vertical in this case are absorbed by the filter, and only the beam of polarized light is allowed through the filter. Now, unpolarized light can also be polarized due to the reflection from surfaces such as water. Water reflects light so that the reflected light has its vibrations concentrated in a plane which is parallel to the water's surface. And so this is the effect of light being reflected from the surface of water. The light coming from the sun is unpolarized, so the direction of energy transfer is along here, but the actual vibrations of the electric and magnetic fields are in all possible perpendicular directions relative to that direction of energy transfer. But when it hits the surface of the lake, only the vibrations of light which are parallel to the water's surface are actually reflected. And this is why even though the images that you see on the surface of very, very still water are identical copies, just reversed copies of the objects that they reflect, they do look different in terms of their kind of brightness and color. And this is the consequence of polarization. So light reflected from a lake, for example, is polarized in a direction parallel to the water's surface. Polaroid sunglasses, I mentioned before, make use of this effect. So on sunny days, the reflected glare reduces visibility and makes people squint. Glare is caused by light reflected from a shiny surface such as water. Now, reflected glare is composed of light which is horizontally polarized. And so here we can see horizontally polarized light, and this can be blocked by wearing vertically polarized sunglasses. So a pair of polarizing filters can be used together to completely block out light. So the filters are first aligned so that as much light passes through them as possible, and then one filter is rotated so that its orientation is at 90 degrees to the other one. So the first filter blocks out light, for example, in the horizontal plane, and the second filter will block out light in the vertical plane, which means ultimately that no light will pass through the second filter. So if we imagine this is our first filter with vertically oriented molecules here, and this is our second filter with horizontally oriented molecules, unpolarized light is hitting the first filter, which only allows the vertically polarized light through, and then when this vertically polarized light hits the second filter will not allow any light through. So even though if you were to look through either of these filters on its own, you would be able to see through them, because some light is passing through. If you put them together, they effectively both together will block out all light from passing through them. Now, when you get to A-level physics, you can do some rather interesting experiments with polarizing filters, which I won't get into here. But For the moment, polarization kind of takes you a little bit beyond the GCSE spec, but I thought I'd mention it here just for kind of the sake of completeness and to give you guys a little bit more of a deeper understanding of electromagnetic waves in general. Now, as I say, we're going to be going over those as well as sound waves, ultrasound, X-rays, various others through the next few lessons in this topic. But for the moment, I hope that that's answered the questions that some of you asked prior to this lesson, and but I can see also that some of the students in attendance have also asked a number of questions in the Q&A box, so I'm going to stop the lesson there and I'm going to go into the Q&A section. For the moment though, I hope that was useful to you, and I will see you in the next one. Take care.